So, welcome to the afternoon session. We're going to have two speakers today before the afternoon coffee. So, the first one is Predrag Popovic at the University of Chicago, and is interested in ice dynamics. And is going to talk today about apparently the very simple rules that govern Aztec marathon patterns.
All right, thanks. Thanks for having me. Hopefully I'll be able to explain at least some of the features that we already observed about melt pond geometry. Okay, so first I'm going to tell you something about melt ponds. Probably all of you already know what melt ponds look like, but just so you know, and I'm going to tell you these observations that other people like Ken and Don have already made, and that's what we'll try to explain. And then I'll give you a model, which is a really, really simple model. Doesn't have any physics inside, and it does explain these features, and then I'm going to tell why. So here's a picture of melt ponds. It was taken from a helicopter during the HOTRAX mission in 2005, and I think this is a pretty good picture because it shows all of these different features that are so prominent on the ice in the summer. So you can see the black ocean, you can see the white ice, and you can see these blue ponds. And obviously, the fact that they're blue is why we care about them, or why some people care about them. Apparently, they're not going to solve global warming, as we heard in a couple of talks. But they are important for some things, and they form these very characteristic, complicated shapes. They have a certain scale. So for example, okay, you can see that this picture is around 400 meters. There's an Olympic-sized pool here in the corner, just so you can see for scale. So you can see that the ponds have some typical scale, maybe a couple of meters, couple of tens of meters across. So even if I take out this pool over here, and if I put a white box around this arrow, you'll still be able to figure out how big the picture is. And this scale probably comes from the scale of the winter snow dunes. So melt ponds are basically anti-correlated with the locations of those snow dunes. And these are the observations that were previously made about their geometry. So mostly people care about the pond coverage fraction, but some people actually made some more detailed studies, like Ken's group, and Ken already talked a little bit about this. So they made this striking observation that the fractal dimension of the pond boundaries, which is really just this exponent which relates the perimeter of a pond to its area, transitions from 1 to 2 at some particular scale, at some particular pond size. So this seems kind of very mysterious and fundamental because these limits are actually mathematical limits which cannot be exceeded by any shape on a plane. 1 just means that the ponds look like simple things, like maybe circles. 2 can mean that they have these like very complicated shapes, maybe like space-filling curves, but maybe also like rivers. It just means that the area is proportional to the perimeter. Then we have this other observation, which Don made, and also other people have made independently, and this is that the pond size distribution can be pretty well approximated to the power law. So these are the two observations that we have, and we'll try to explain them with this void model. And this is the model. It's extremely simple. So on Ian's, well, that's all right. On Ian's scale of model complexity, if reality were here and SCMs were here, our model would be around here. Very, very simple. There's nothing inside. It's just no dynamics, no physics, just geometry. So the model works like this. We start from a plane and we throw around circles, and the circles can have different sizes, and then we let the circles overlap, and once we place enough circles, as much as we want, we look at these voids that are left between the circles, and we say, okay, those are ponds. and the circles are ice. So physically, some vague motivation for this might be that the circles are maybe like these snow dunes that form in the winter, and then this what's left between them is are ponds. This is what it looks like. This is like a real image. This is what the model gives. It kind of, there is some resemblance, but maybe it's not that obvious. But statistically, they are actually very, very similar. So the model has only two parameters. One is the scale of the circles that we throw. So this is a necessary parameter in any model, geometric model like this, because we need a way to map this geometric model onto a natural system. And then the other parameter is just how much of the surface is covered by these voids. And then these circles that we throw around, we draw their radii from some distribution, which shows an exponential distribution. So this is kind of a schematic. What it looks like, we draw a bunch of small circles, then a couple of big circles, and then no circles beyond a certain size. And so it turns out that this is the only important thing. So the form of this distribution doesn't really matter. We can use anything, and even just using constant radii, circles of constant radius is almost good enough. But the important thing is that we don't go beyond a certain size. And so we need a way to choose these parameters. Obviously, we want to do it by comparing with data. And so we analyzed a bunch of images from the Shiba mission and the HOTRAX mission. We split the images into ice and ponds. So this is an example. And then for every date, there were a couple of dates available. For every date, we got around 100,000 ponds. So there was a lot of data. And we chose to choose this scale, R0, the scale of the circles, by comparing this, we call it the two-point correlation function between the data and the model. So this function is really just quantifies the probability that 2 points, which are separated by this distance d, are both located on a pond, given that one of them is already on a pond. So basically, we randomly choose a point on a pond, and we draw a circle around it that has a radius d, and we count the fraction of the circle that falls within a pond, and then this is the value of, and after we average over all of these points, this is the value of the this part of the correlation function. So it's kind of constrained. It cannot be anything. So if d is equal to 0, then this probability has to be 1. If d is equal to very, very large, then this probability has to be the coverage fraction. So we can kind of remove this dependence on the coverage fraction if we subtract the coverage fraction and divide by the ice fraction. So these two scaling additions basically just remove the dependence on rho. And so this two-point correlation function, it's basically a measure of the size of these features. So this is what you would think when you say ponds have a scale of 10 meters. So you would think that this function drops to 0 after maybe 10 meters. And it doesn't depend on the coverage fraction, which makes it a good measure of just in the model at least, it just depends on this parameter, the scale of the circles. So these are the possible shapes that the function can have. In the model, we expect this red curve because there is no correlation between, we're just randomly throwing circles. In the data, it might look something like this or something else. So if it looks like the blue curve or something else, then maybe our assumption of just randomly placing circles is not that great. But this is the comparison of the two-point correlation function for the data and the model. So black line is the model, and all of these other colored points are the data. So obviously, the exponential drop-off is reproduced really well. So I think our assumption of just that the ponds aren't interacting among each other, that's a good assumption. OK, so we need to choose this other parameter. And so the coverage fraction in the model. And we need some metric which is sensitive to this parameter. And we're going to introduce this cluster correlation function, this other type of correlation function which is sensitive to rho. Okay? So it's basically the same thing. It's just the only difference between this and the previous one is that this quantifies the probability that 2 points separated by a distance d are located on the same pond. So this is kind of what we'll expect this function to look like in a model. So beyond the scale that the scale of these individual features, this function depends on how far away we are from the so-called percolation threshold. So this is in the model, what we would expect this to look like. So the percolation threshold is just the coverage fraction for which we start getting infinite clusters. So if you obviously, if you fill enough of the surface with these random voids, then you will get an infinite connected cluster. And so if we are right at this point, then this G of D will be just a power law. If we're away from this point, it will be a power law up to some point and then drop off exponentially. And if we are just focusing on the finite ponds, so not finite voids, not the infinite ones, then it doesn't really matter if we're above or below this rho c. Okay, so this is how this depends on rho in the model. In the data, this can really look like anything. Okay, and so I should say just one thing, which in reality we will always see something like the blue curve, because even if we are close to the percolation threshold, this cutoff will still be set by the image size at least. Okay, so it can be anything in the data, but it turns out it's exactly like the model. Okay, so this is the data. The red dots are the data, and then this model is the cluster correlation function for the model, and it can be well reproduced by this range of rows. And so we chose this row to represent sort of this connectedness in the ponds, and it doesn't really have to do anything with the actual pond coverage. But it turns out that the actual pond coverage is also around 30%. So it's kind of maybe a coincidence, but and when we were doing this, so the motivation was just to calibrate the model, just to choose these two parameters. But we found two very surprising observations, which I think observation people might want to look into more. So maybe it's a coincidence because we only have two different missions. But if they collected more data, maybe this would turn out to be something more general. So we have two missions. One was the Shiba mission from 1998, and the other one was the HOTRAX mission from 2005. Okay, and if we plot the 2-point correlation function, so just the size of the individual ponds, it's exactly the same for the 2 years. So even though they may be developed under very different conditions, it seems exactly the same. So that's very strange, and obviously not within the scope of our model, but something that someone might want to look at. If we look at this other function, it turns out, so again, the yellow dots are 2005 ponds, and the red dots are 1998 ponds. And it turns out that both are really reproduced by the void model using the same range of rows. And the only difference between these is the image size. So if we use the void model and set rho equal to 0.3 and use the image size of the Shiba images, we get this curve. If we use the same row and use the image size that was in the HOTRAX mission, we get this curve. Okay, so that's surprising observation number one. 2 years which had, probably very, very different conditions, have very similar ponds. The other surprising observation I kind of already said, I just didn't really say it, is the fact that this is really set by the image size, this cutoff. So I talked about how this cluster correlation function should depend on the on this parameter rho, And the fact that this cutoff is set by the image size really means that we are close to the percolation threshold. And this is also reflected by the fact that that these curves can be fit by a whole range of rows, not just a single row. So this means just that this correlation length is larger than the image size. Okay, and if you don't really buy this argument, we did an experiment independently. We ran the model several times, something like 100 times for each coverage fraction. And we found the probability of finding a cluster that goes from one end of the image to the other. And so for low coverage fraction, it's 0, right? For high, it's 1. But between 0.27, so this line, and 0.32, it transitions from 0 to 1. So this is the second very surprising observation, is that the ponds somehow seem to be right at the percolation threshold. So we were pretty surprised by this. And again, our model cannot account for this, but so it needs physics. And it's something to be looked at. Maybe it's again a coincidence or some artifact of averaging over many images. And then we can use these R0 and rho, and we could look at the fractal dimension. So the thing that really motivated this project. So the way we find fractal dimension, it's sort of the same thing as Ken does. We fit a function to the area and perimeter data, and I'm not going to talk about that in detail, but this is the result. So all the red lines are the data from the Shiba mission, and then the dashed line is the model. And so, okay, we have no tuning parameters. We already chose our parameters by choosing those correlation functions, but these two things match nearly perfectly. So main result number 1 and main result number 2, the same thing happens more or less for the size distribution. And it's not just reproduced, it's reproduced over the entire observation range. I mean, apart from maybe small deviations there, but like maybe 7 orders of magnitude. Okay, why? Well, the main reason for this is that, well, any model that represents ponds as objects that have a typical size and that connect randomly will reproduce these universal geometric features. So any model, so two criteria, 2 ingredients that any model, if any model has, it will give this. So randomness and scale, or size, typical size of the individual objects. And those universal features are, for example, the correlation function, the 2-point correlation function is going to be an exponential. The cluster correlation function above the scale defined by the 2-point correlation function is going to be a power law, and we're going to reproduce the power law exponent. There is going to be a fractal transition from some low d to d equals 2. And we're going to reproduce the size distribution also and also it's going to be a power law, and also the exponent of the power law is going to be good. Apart from these universal features, there are also these non-universal features. For example, if we match the correlation function, it's not obvious that we also have to match the scale and the width of the fractal transition. So the fact that our model does this is kind of why we chose it. And then, for example, for small ponds or small clusters, below the 2-point correlation length, the cluster correlation function doesn't have to be universal, and then the size distribution doesn't have to be universal. And then the percolation threshold doesn't really need to correspond to what the real pond coverage is. So the fact that our model really reproduces all of these non-universal features is why we chose it instead of any other model. I'm going to show, for example, how this works for the fractal transition, because I think this is sort of, in my mind, this was the most mysterious property. So this sort of, it's a qualitative argument, but I think it's right. It's going to have two steps. So first, I'm going to show that the void model can be thought of this collection of objects that connect randomly. And then I'm going to show that for such a system, the upper fractal dimension must be 2. So, OK, so here's how we start. Throw around points on a plane. And these points, so those are these points. And they're going to be considered, they're going to be the circle centers. But we're not going to draw the circles yet. We're first going to segment this surface into these regions, these polygons. And the polygons are really regions. So each point on this polygon is closest to this circle center. So it's basically just regions of space which are closest to one of the points. And it turns out that this is kind of a natural grid for this void model. Then we can draw circles, and we can erase all of these edges of these polygons if they cross a circle. And what this leaves is this kind of a skeleton which goes through these voids, and it turns out that this has a very, very wonderful property that the connected edges, connected bonds on this skeleton also correspond to connected voids. So in this way, we have kind of discretized the problem. So it seemed like a complicated, continuous kind of a problem, and now it's kind of less continuous. It's kind of more discrete. So we can use kind of this construction, and we can, and then to each of these bonds, we can kind of assign a piece of the void. Okay. So we can do this in this way. So for example, this bond will contain this piece of the void. This bond will contain this bit. And so the total area of a void and the total perimeter of the void will be a sum of contributions from these individual segments. Okay. So these segments, so the contributions from these segments obviously vary a lot. But the important thing to note is that, yes, they vary a lot, but they don't vary beyond a certain size. So there is a limit to how big this can get, how big a contribution due to a segment can get. So if we imagine, if we're looking at a large void, so something that has a large connection of these bonds, so right over here, then it doesn't matter if individual contributions from these voids differ a little bit. It's kind of going to average out. And so the variation in the area and perimeter of these large ponds or large voids is going to be mainly due to different numbers of these bonds in a void or well, individual ponds or whatever that may be. So this means that the perimeter and the area are both proportional to the number of bonds in the void, which means that they're proportional to each other, which means that the fractal dimension is 2. Okay? So basically, okay, so the first step, we showed that the void model was just a collection of connecting objects. And then the second step, if you have a collection of connecting objects for large enough clusters, you're going to have an upper fractal dimension of 2. It has to be. The lower fractal dimension doesn't have to be 1. And in fact, I think in the void model, that's one place where it kind of disagrees. It's kind of a little higher than 1. But you know, if the individual objects are simple, how much time? Okay. If the individual objects are simple, it's just gonna, we can easily make it 1. Okay. And so this also gives the criterion for when the transition will begin and when it will end. It will begin when the size when these objects have more than one of these connections, and it will end when the contributions from these individual objects kind of average out. And okay, so I'm going to give a couple of examples of all of these different models which might give the same geometric features. So okay, here's a melt pond. We see it in the void model. For example, just overlapping circles. It's also going to give the same universal characteristics. Ken talked a little bit about the random topography. It's also going to give the same same universal characteristics because of it having these two ingredients, which are just the randomness and the scale. And apart from these, in geometric models, we also we can make dynamical models which kind of do the same thing. So for example, the icing model that Yiping Ma is going to talk about after this and that Ken's group has been working on, also it has these two ingredients, and so it is going to reproduce the universal characteristics. And this last one is just, if we start off from a random configuration of zeros and ones and just smooth the image a couple of times, then we get something like this. Okay, so all of these fall into the same class of models which give the same features as melt ponds. But I just want to say a couple of words about these two. First of all, they're sort of in a class of their own. They're models of coarsening. So basically, each point becomes a 0 or a 1 depending on its neighbors. So if there are more 1s around it, then it becomes 1 more likely. So they're sort of the same model. And when I first thought about this, I didn't think much about it. But then I thought a little bit more, and it turns out that these models can actually do something that we have observed that is not, we found one of those surprising observations. And this is that these models actually give the pond cluster structure right at the percolation threshold very naturally and with no tuning. So I think, so this, what Yiping and what Ken's group is doing and what Yiping Ma is going to talk about, I don't know if their dynamics are right. And I mean, I don't even know if this is the right way to go, but I think that these models might actually be on the right track because they explain this thing which we found really surprising and didn't have other ways of explaining. And then also they really look like melt ponds. So, so these are the conclusions. We made this really simple model which explains all of these features, and it doesn't take any tuning parameters. We found two surprising observations. One, that ponds seem to be very similar to each other, even though they're from different years or missions. And then second, that they're near the percolation threshold. And then finally, that we gave the ingredients that a model must fulfill to, in order to explain these features. That's it.
We got time for one question. Okay, two questions.
Do you want to go first? Can you explain what we can learn from your findings for large-scale modeling, considering that we are not interested on individual ponds, but just on the total fraction which is covered by ponds?
I don't think this is important for a total fraction of ponds. I mean, it does have some. I think for me, this was more like science for the sake of science. It's not, I wasn't really trying to answer those. But I think, I mean, pond geometry, I think, has some consequences, for example, for lateral melting of ponds. So it depends on, say, if you know how much perimeter you have, that's going to change the rate at which the pond growth by lateral melting is going on. It can tell you something about maybe breakup of the flows at the end of the summer, something about the light field beneath the ice. Those are kind of the consequences, I think, practical consequences, I think. And I think like maybe if someone can make a good simple dynamical model, then that might actually have direct consequences for modeling the pond fraction.
Sorry.
Not me.
Nick.
Just in the model, the density is the density of ponds within the domain. That's direct. That's just defined by the scale length.
Say again?
So can you go back to the equation if you don't mind? Yeah. So the density of the pond. So your only parameter there is the scale length, but not a pond density.
Oh no. So the only parameter for the distribution of the radii, but kind of this other parameter is what fraction of the surface is covered. How many ponds? How many of these circles do you throw around? So these are what size of the circles and how many do you place?
Right. Yeah. I know. I just missed that.
Okay.
Because that might explain why it's necessarily at the transition. Let's say that if that density is much lower, then you're not going to get anywhere near the percolation transition.
Well, right. The thing is, I mean, we can we can tune this parameter. It's going to. So if I place this parameter lower than 0.27, this curve is going to cut off lower. If I place it higher than 32, it's also the same thing is going to happen. But the thing is that the density that matches the data seems to be right at the percolation threshold. That's
which is true for like theoretical percolation models. Well, yeah, around 0.3, right?
For say,
is it normally like 0.3 for a 2D percolation model?
Well, it depends on the model. It's kind of one of these things that depend on the model. So for example, for overlapping circles, it's 70%. For this, it's 30%.
Thanks.
Yeah.
Quick question.
Okay, super quick. Very low time talk. Really enjoyed it. Okay. Your model doesn't have any much to do with melt ponds really. So could you just apply it? I mean, it's very interesting, these general properties of topography. Why not apply it to pressure ridges or some other surface feature?
Possibly. Yeah, maybe. I think they're kind of like, I don't know any observations about ridges, but maybe there are some things, maybe not the same model, but I think like a lot of things can be described with a simple model that doesn't really need any physics.
So thank you, Predrag.
Yeah.
And what is getting set up?